So let me begin by thanking the organizers as well. This kind of thing is a lot of work. It takes personal time, it takes attention span, but they're also really fantastic for the community. So thank you for putting in the time to do that. So I'm very happy to be here and tell you about, I wasn't sure what I was going to talk about. Today I decided in the end to focus on some experiments we do with matter wave interferometry and Hamiltonian engineering in a Kavli QED system. This work is at JILA and NIST and the Department of Physics at the University of Colorado. Great. So, well, we've already heard the basic idea here is that, well, we can have these atoms, individual atoms, we can laser cool them, we can remove the entropy from the internal state, we can remove the entropy from the external state, we can make them do whatever we want. But wouldn't it be great if we could create correlations and entanglement between them? The way we're going to do that in our experiments is by having two very reflecting mirrors to form an optical cavity. Light's going to bounce back and forth many times. And it's going to create sort of connections between the atoms. We are not going to be interested in the light field. The light field is a tool. All the interesting stuff is going to happen inside the atoms. And in particular, what we do is we use all of quantum mechanics, so not just unitary dynamics and dissipation, but also the quantum measurement process in order to do interesting things. Okay? Broadly, the themes of our research is exploring the fundamental science of quantum sensing, metrology, and many-body physics. So let's jump in. We actually have 4 cavity QED systems running in my lab. Here are 3 of them. 2 of them are in strontium. 1 is rubidium. This is, for instance, laser-cooled strontium. Here's a mirror, here's a mirror. That's about 5 centimeters in between big macroscopic cavities. Okay. The single particle cooperativity, which in some sense drives almost all of this physics, is of order 1. So single particle physics is not going to be interesting. Everything is going to be driven by collective physics. That's where it's at for these experiments. Okay. In addition, we have this 2 centimeter spacing rubidium system that's vertically oriented. We have a ring cavity. If you squint, you can see laser cooled atoms cooled into this ring cavity mode right here. All right, so we love all of our children equally, but unfortunately I can't tell you how wonderful they all are today, so I have to skip over some of them. And in particular, I'm going to skip over how we've been thinking about emulating dynamical phases of BCS superconductors. We've seen some really cool stuff where we can sort of engineer very straightforward Hamiltonians with the idea that we can add complexity in controlled ways in the future. For instance, we've been able to show that we can do the equivalent of measuring what was called the spectral gap in the early days of studies of BEC, where you're in BCS physics, where you're basically trying to understand what's the sort of the pairing amplitude in the system, but you can make all these really nice analogies there. We think this has a lot of legs. It's going to be a lot of fun. Well, actually, you just heard about this one from Anna Maria, this collective dissipation leading to steady states. We have a project where we're trying to create ultra narrow line with laser light using the process of superradiance, and we've seen that in a pulse mode. These pulses of light are actually the most stable active atomic clock that's ever been realized. Okay, turns out that these are very, very stable in frequency pulses of light. We'd like to turn that into a CW system. Okay, so we could actually start probing things like general relativity on very fast time scales. Okay. I'm not going to tell you about that. Okay, there is something that could be a fun discussion. Actually, Helmut has been involved with this work, where we have seen in a strontium ring cavity system a very weird thing where there's something called collective atomic recoil lasing, which is a lasing essentially between momentum states, between ground momentum states. Normally, you see this in a pulsed way. Actually, this can run for hours. It's just a CW mechanism, and we can study it. I don't have time to talk about it, but it's on the archive here. And lastly, I really want to emphasize that we have really exquisite control. So for instance, here we are using the cavity to directly observe absorption on a millihertz line with transition in strontium. This is one nuclear spin transition. Here's another nuclear spin transition. The scale here, each of these sort of dashes here is 100 hertz. Very, very narrow. We have a lot of control in the system. In addition to sort of some interesting multi-level dark states that would be cool to build, we also have some ideas about how to build what I'll call a dark laser, which is basically how can I use measurement and feedback to extract information from a laser about its phase without actually having the laser emit light, or at least as little as possible. Okay. So I'll point you to sort of these references. So I've told you about the children I'm not going to talk about today, so let's talk about the ones we are going to discuss. Here's sort of the plan of attack over here, and let's just jump in with this idea of squeezed matter wave interferometry. Okay, so there are these squeezed states. The basic idea is if I have a collection of n atoms in precision measurement, we always think of mapping to spin halves, some ground excited state. And then we say if I have n of them, I can put them tip to tail, form a collective block vector over here. And you ask, where is that block vector pointed on the block sphere? That's what a precision measurement turns out to be. It's just estimating what's the angular orientation of this collective block vector. There's some quantum fuzziness, okay, in the actual orientation of that. This is kind of like the vacuum noise for spins right here. And so you can say there's an angular uncertainty, which is 1 over root n radians. It has units of radians. Okay, when we say 1 over root n, we mean 1 over root n radians. It's an angle. Okay, that's what you should have in mind. And your ability to estimate this phase, which then is what you're going to use to estimate the amount of phase that accrued, say, in a Ramsey sequence. That's why it's relevant. So the basic idea is if I don't have an entangled atoms, this is the best I can do. If I entangle the atoms, you can generate these states, which we just heard about, called squeeze states, where you can actually have enhanced angular sensitivity. And once you see that, you also know that you're entangling the atoms in order to do that. Essentially, the atoms have to cooperate with each other in order to partially cancel each other's quantum noise, fundamental single particle quantum noise. Here's a list of sort of entangled states that take you beyond sort of the standard quantum limit. This is the directly observed spectroscopic enhancement. 1 means no entanglement, higher, log scale. This is invariant, means better. Ion traps, cold gases, collisions in cold gases, for instance. Squeezed light, just to put it on the same scale here, Roman Schnabel. These are about the best you can do over here. So the work in my lab are the red points over here, and basically the most entangled things that people have been able to realize are using cavity QED techniques, in particular something called a quantum non-demolition measurement, and Mark Hasovich's group at Stanford and our group. These are some of the most entangled states ever generated, bar none. It's not in superconducting circuits, it's not in Rydberg systems. Pick whatever your platform is. It works remarkably well, is I think what I'm trying to tell you, okay? It seems like a weird thing, this weird thing these QED people are doing. It just works really well, okay? So recently, and I'm going to tell you about this one, we were able to realize an entanglement enhanced matter wave interferometer for the first time. Briefly, I'd like to tell you also about how we made a differential clock measurement that was enhanced by squeezing. This was in collaboration with Jun Yi's group, where I helped them to sort of take the ideas that we've sort of figured out in my lab and apply it to a clock. In particular, they have a cavity. And essentially what they do, what we do in that system is we sort of call this little clump of atoms clock A, this ensemble of atoms clock B. We use the cavity, perform something called a quantum non-demolition measurement to create a squeeze state. We shuffle the atoms up, create a squeeze state, and then we run a differential clock between them and see that we get an enhancement in the system. So if you're interested in that, you can look in this reference over here. I'm going to tell you about light pulse matter wave interferometers. This may not be your thing. It's not the thing you do. So, you know, the basic idea is if I have some atoms, they're sitting in some vacuum chamber, they're just sort of flying along, I can get the atom to go into a superposition of having absorbed a photon or not absorbed a photon, okay? And so if it doesn't absorb the photon, it just keeps going in the same direction. If it absorbs, it actually has a recoil because light carries momentum, h bar k. So in fact, you can sort of build this, you know, analog of an optical interferometer, but with the matter waves themselves. You can actually get interference at this last point here where you apply sort of the equivalent of a pi over 2 pulse to get an interference term. Really, really important for measurement science, for technologies, as well as for fundamental physics, including future you know, ideas for detecting gravitational waves in space. And in fact, I'll just point you to this paper where we really analyzed these sort of proposals, and you can really map them onto thinking of the atoms as a quantum memory, is what the role of the atoms are in these systems. Okay, so our entangled matter wave interferometer is that we should think of it on a block sphere as if the atom is going along one arm versus the other, we'll think one of these is spin up, one is spin down. We'll describe the whole interferometer on a block sphere over here. So the idea is that somehow we run a little mini interferometer, we create squeezing during that mini matter wave interferometer. Unsqueezed, see, my fist is round, that's unsqueezed. Squeezed, see, my hand is thin this way, so that's squeezed, right? So after having created that, what we do is we hit the system with pulses of light that essentially acts like a pi/2 pulse that's oriented along the block vector that causes the state to rotate through pi/2. That starts the sensing phase. That's what happens right here. Then you run your real interferometer, you accumulate some phase, you hit it with a final pi/2 pulse, you map that phase onto the population direction, which is JZ. And now you have enhanced sensitivity in your ability to estimate the phase that accrued inside the interferometer. Okay. In order to do that, we do this in rubidium. We have a vertically oriented optical cavity. We laser cool atoms inside of it. We have a repulsive optical dipole trap that we form. It's like a donut trap that guides the atoms as they are free to fall along gravity here. And here are some cavity parameters for this system. So we need to manipulate the momentum states. This is in part for terminology. If we apply along the cavity axis two tones that have the right frequency separation, we can actually change the momentum of the atom, but also flip its hyperfine state. And then we can actually continue to sort of apply various pi pulses and create some momentum separation that we can then detect. So we can manipulate coherently the momentum states of these atoms as they move along the cavity axis. This is called a Raman momentum transfer. There's also a version called Bragg momentum transfer where you don't change the hyperfine spin state, you just change the momentum state. So for instance, hit with the pi/2 pulse, and then you could hit with subsequent pi pulses to move this part of the wave packet further away in momentum, and we can actually build those states and detect them over here as well. These are the basic tools. These are like your beam splitters of your interferometer. And this had never been done in a high-finesse cavity like this, so we've got that. So now we can actually construct a Mach-Zehnder interferometer with those pieces. And we can see interference, great, when we vary the phase of this final pi/2 pulse. And we can actually see that the phase that accrues as a function of time goes like t squared, where t is sort of the time of the Mach-Zehnder interferometer. It's the same scaling you expect if you drop a rock, okay? You know, the distance it falls goes like t squared. So this says actually we're sensing accelerations in the system. Cool. Now the part I'm not gonna explain to you, but I'll just tell you the basic idea. We essentially go into a limit where the cavity is far detuned from the optically excited state. So we work in a dispersive limit such that the cavity resonance frequency shifts by an amount that depends on the number of atoms in spin up over here. And by doing that, we can actually count how many atoms are in spin up without telling which atoms are in spin up. And that preserves every atom as remaining in a superposition of spin up and spin down. We only gain collective information and not single particle information. And that's the key point. By making that measurement very precise, you can think of it as measuring number of atoms in up as equivalent to measuring the spin projection JZ over here. And so what that allows us to do is make a measurement that's so precise that we can actually localize the state into a range of angles that's smaller than the original standard quantum limit angle. So we just measure it and localize it. Okay. Cool. If we optimize our measurement, we see that we can drop below the standard quantum limit in our angular resolution over here. So with that, we actually have, while we're using the spin states to sort of ride along with the momentum states in order to help us have the cavity distinguish those two states. Nevertheless, the momentum states are involved, and we see 3.4 dB of directly observed squeezing, but with the momentum states involved. Previously, we'd done it with just spin degrees of freedom involved, no momentum states, and there we could get to 18 dB. But this is the first time getting it with the momentum states involved, which is what you want for matter wave interferometry. So that's one approach. The other approach is to take that same Hamiltonian and actually turn it into more sort of a dynamical process. And the basic idea is, here's your cavity resonance frequency, and I'm telling you your cavity resonance frequency actually depends on the spin projection JZ. So it actually, from shot to shot, it will take on a different value. So if I just drive the cavity with some tone over here at fixed detuning, it's always the same frequency. What I'm telling you is that the amount of light that will get into the cavity depends on the detuning from whatever the resonance frequency is, and therefore the number of photons inside the cavity depends on the spin projection Jz. So then I can take my QED Hamiltonian over here, and I can just say, well, let's let C dagger C be a function of Jz, and I get what's called a one-axis twisting Hamiltonian. It works. It turns out this is basically the physics. You got to get the factors of 2 right, but this is basically it. If you do that, what does this do to you? Here's your quantum noise distribution on the Bloch sphere. Think of it as a classical quasi-probability distribution for the moment. It causes a shearing. Bloch vectors above the equator rotate one way, Bloch vectors below the equator rotate the other way. It shears the quantum noise distribution into a squeeze state over here. And so we can go look for that. We apply this shearing operation, and then we actually sort of rotate through some small angle alpha, and we look at the noise along the spin projection Jz. This takes many trials to map out the noise of the system, and we see that we drop below the standard quantum limit over here. Here it's about 2.5 dB of directly observed squeezing with the momentum states involved. So we have these 2 different approaches for doing it. You might ask which one's better. And so we actually tried to write a somewhat general paper that tried to compare the 2. And basically the idea is that in the QED measurement, you need to detect the light coming out and extract information from it. And if you can make the total real, like total quantum efficiency associated with that process bigger than 3/16, actually QED wins, okay? If it's below that, then actually you should use this kind of like unitary dynamics to make up for the fact that you can't build a good detector, okay? And so that's in this paper here. Okay, I'm just going to conclude by saying not only can we generate this squeezing, but we can actually inject it into a full matter wave interferometer, measure at the output, and actually see that we get an enhancement in the phase precision of the interferometer at the output. So this is the first time a full matter wave interferometer was run, where you can actually see that you can push the entanglement through the interferometer and get it out the output. So we think this is a very important first step in these systems. Now I'm going to switch gears. Let's go to topic number 2 here. Momentum exchange interactions and a new collective recoil mechanism. I just told you about physics where we were labeling the momentum states, 2h bar k, that's 2 photon recoils because they're 2 photon transitions, and no recoil here, spin up, spin down. What if we could get rid of the spin labels altogether? So it was just like the average momentum and then plus h bar k and minus h bar k labeled my north and south poles of my Bloch sphere. Can I do that? It turns out we've been thinking about, sort of spin systems in our group and in Monica's group, Schleyer-Smith's, more recently in Tillman Esslinger's group, which inspired some work at Gilla thinking about for matter wave interferometers in a Bragg regime where you don't have spin labels involved. And it turned out that that then came back and inspired us to think about this. So it's a really sort of nice spiral there. And so it turns out we can, and the basic idea is that you can get a cavity-mediated momentum exchange interaction, where if I think of my 2 momentum states as the average momentum, because actually we're going to let the atoms fall along gravity, that's what P naught is, plus h bar k minus h bar k, I'll call that, say, spin up and that spin down. You can have a process where we apply a dressing laser into the cavity that allows the blue atom to absorb a photon, emit it into the cavity. Before that photon has a chance to escape, the red photon, the red atom gobbles it up and flips its momentum state. So that looks like I sort of, lowered the spin state, if I think of these as pseudo spins over here, of atom I and increased the momentum state of atom J. But it's all to all because it's through the cavity. So you can write this in terms of collective raising and lowering operators. So it really looks like a chi J plus J minus term. Okay. One way to think about this is that we're placing atoms in a superposition of 2 different momentum states. So here's the wave function associated with that superposition over here. So in position, that means we get a sort of a density gradient of where you find the atoms. And so you have some density gradient along the cavity axis of where you find the atoms, and that's moving at some velocity p naught over m downwards because we let the atoms initially fall under gravity. So now let's imagine I'm injecting light from below, then that light is propagating upwards. But it turns out, for the experimentalists in the room, if you go to Thor Labs, we know that we can buy Bragg mirrors. Just alternating layers of dielectric constant. And that's what essentially this standing wave is. Essentially where the atom is if it's coupled to the cavity, it presents some index of refraction to the cavity that shifts its cavity resonance frequency. But alternatively, you can think of this as like a little bragg mirror. And so that pump can actually scatter off of it and emit a photon into the cavity. But because it's a moving bragg mirror, it's moving downwards. When I backscatter, I get a Doppler shift in that backscattered photon, and I get a blue sideband. There's the other process where the pump light is, or the dressing light is propagating downwards. When I backscatter off of that one, I get the opposite Doppler shift, and I get a red sideband over here. It turns out exactly the combination of this carrier plus that sideband creates a coupling between the two momentum states, and that's what drives the interaction in the system. That's what's going to give rise to the exchange interaction. It's collectively enhanced because I have N atoms, and so what happens is you get a collective enhancement or phase coherent addition of the electric fields of these blue and red sidebands being scattered off of each atom. So that actually gives you sort of the rate at which that happens goes like N squared, and that's sort of the superradiant collective enhancement for this process. That's why NC is what matters for this process, the collective cooperativity. Great. So what are the dynamical consequences of this? I can rewrite, at least keeping only collective terms, J plus J minus is total J squared minus JZ squared over here. And so what that means is that actually this JZ squared actually should give you one-axis twisting. So we can actually see that at the mean field level. I won't go into details, but we can actually see this sort of shearing process, but at the mean field level so far. But we can harness this for creating entanglement in the future. But I want to tell you this weird one, which is if I don't have the interactions applied by just not applying that dressing laser, then after our first pi/2 pulse, the two atomic wave packets begin to separate from each other, the two momentum states. And what we see is the black points that the coherence, in other words, if we apply another pi/2 pulse, sort of how much degree of interference do we have, goes down. And why? Because the wave packets, actually like this, are separating in space. So they don't overlap with each other. So if I apply some pi/2 pulse, they just can't interfere. They're not spatially aligned to each other. And so that sort of goes down here. But if we turn the interactions on, we see the red points. What's going on? It's kind of like saying, look, in a matter wave interferometer, the wave packets like to separate, but we're telling you that we see coherence, which means the wave packets are not separating anymore. Okay? So, well, are the wave packets like glued together? Are they connected by a spring? What's going on? Here's actually a numerical simulation from Anna Maria's group. If I have the interactions off, this is all the cavity axis is along the horizontal, the two wave packets separate. Let's run that again. If the interaction is on, oops, hopefully, maybe I just have to go back and come forward. If the interaction is on, you actually see that you maintain the interference because the two parts of the wave packet don't separate. Okay. Is it a spring? Well, I know how to tell if something is a spring. I'll push on it and see if it rings. So that's what we do. We allow the wave packets to begin to separate, and then we turn on the interactions. And now, actually, you might imagine if it's a spring, the wave packets do this. So you should see the contrast or the sort of interference term go up and down, and that's exactly what we see. Turns out the spring characteristic frequency is just chi times n, where chi is this sort of same coupling that was talked about by Anna Maria in the previous talk. Okay? Oh, it's the afternoon, lunch was good, maybe not enough coffee. So let me try and summarize this, because you're going to forget. What are we looking at here? Let's try and understand what's going on here and tell you how weird it is by doing a Gedanken experiment. Let's imagine I have N atoms, and they don't have any interactions. I have a single photon gun. You know, pew, I shoot a photon out of it. What happens? It goes into the cloud, and if I wait some amount of time, eventually one atom will emerge, and it will come out at a velocity h bar k over m. Let's just assume it's one photon being absorbed. Now what I'm telling you is if I have these momentum exchange interactions, I shoot that photon into the cloud, and the whole cloud recoils collectively. In fact, all of the atoms recoil at the same velocity, h bar k, but divided by n. Okay? So this is actually a lot like what would be, you might think of as Lambdicki spectroscopy or Mossbauer spectroscopy. It's a collective recoil mechanism that's giving rise to this enhancement in the coherence of the system. If you're not familiar with it, it turns out this is like, Mossbauer spectroscopy was important for like the first observation of the redshift of a photon. This Lambdicki trapping is very important for all quantum technologies. associated with trapping atoms and ions and manipulating them in atomic clocks and quantum sensors. So now we're saying we have this new collective mechanism for matter waves, but yeah, maybe it's just this weird matter wave thing. Would this actually work on an optical transition? Well, it just so happens we have in our lab a ring cavity with strontium in it. So we went to the 7.5 kilohertz clock transition over here, singlet S0 to triplet P1. That's the radiative line width. We drive the cavity mode to put each atom in a superposition of the ground state and the excited state. And then we look at the power that leaks out of the cavity as a function of time. And it turns out that we detune the cavity from resonance. It's like a very weak superradiant process. That's what the light is coming out, but it's proportional to the total atomic coherence, the collective atomic coherence. Okay? So we can measure the temperature of our atoms, and we can predict that the atomic coherence, collective atomic coherence as a function of time, should sort of fall off like this due to Doppler dephasing or motional dephasing. But what we actually measure is this. That's the data. And we see that also we're getting gap protection on a clock transition over here. Okay. In the little bit of time I have left, I'm going to tell you about XYZ Hamiltonian engineering. I've told you about how we can engineer a momentum exchange interaction by applying a pump here or a dressing laser and getting some sideband over here that somehow does this magic of creating this exchange interaction. And just to remind you, okay, so if an atom is here, I absorb a pump photon, I emit it into the cavity. Before it has a chance to escape, the other atom absorbs it, they flip their momentum states. That's the J plus J minus term over here, okay, exchange. However, if we apply another laser that's separated by twice the frequency difference between these two states, energy difference over here, we can actually open up another 4-photon process. And in that process, imagine that two atoms start in the same momentum state. You can absorb from one pump, emit a photon into the cavity, but that photon is just sitting in the cavity, so let's draw it on the other leg here. So now the red photon can absorb it and stimulate emit into the other pump, and I've conserved both energy and momentum in the system. So basically now I have a pair raising and pair lowering term as well. So this, we'll call that KITP over here, and that goes like J plus squared plus J minus squared, where these are, again, all-to-all collective operators. And what's important here, I'll point out, is that this term involved two interactions with the same dressing field and two interactions with the cavity. Whereas over here, this involved an interaction with both of the applied dressing lasers. So therefore, it's proportional to the product of the Rabi frequencies associated with those two dressing lasers. So they actually scale differently with those sort of electric fields that we send into the cavity. That gives us a tuning knob. So in particular, we can sort of sum this term plus that term and effectively get a sort of an arbitrary XYZ Hamiltonian by sort of summing these terms together. There's a caveat. This is only true in the fully symmetric manifold of states. Okay. So I'll just show you that, for instance, we can go from exchange interaction to actually engineering a JX squared Ising, all-to-all Ising interaction by setting these two pump amplitudes to be the same over here. These are actually measured flow lines on the block sphere. This is actually data where we actually say if a block vector starts here, where does it move as a function of time? It's a vector map that shows you that, called flow lines. So we can see that we're actually generating that Hamiltonian. Just to give you one other sort of Hamiltonian in the zoo is that you can imagine that you adjust these two relative pump amplitudes. And in fact, by setting the relative pump amplitudes to about 0.06, their powers. It's a very small amount of extra pump light. It turns out you can actually generate what's called the two-axis counter-twisting Hamiltonian, which was originally proposed by Kitagawa and Ueda. In grad school, I was like, God, one day I would love to figure out how to do that. No one's known how to do it. We can do it now. Okay. And so, in fact, we can measure these flow lines. Again, this is data on the block sphere, and we can see that you get 2 bifurcation points on the equator, opposite sides, plus 4 stable points as you go around. And so clearly we're demonstrating that Hamiltonian generating. Okay, so that's the XYZ. Last topic. Perfect. Everything I've told you about, and pretty much everything in collective cavity QED that you have ever heard about, can be described by two-body interactions. Okay, so let's talk about what that means. The basic idea is, imagine, like, as an example, here's a two-body interaction. What I mean by that is if I take these collective operators and I unpack them over here, it's a sum over all atom pairs where it's not the same atom. I is not equal to J from 1 to N. sigma plus I, sigma plus J. See, it's a pairwise interaction. It's summing over all of them. So it's kind of like two atoms flip their spin state at the same time. But it's all possible combinations. That's a two-body interaction. Jz squared is a two-body interaction. Jx squared is a two-body interaction. Does that make sense? Okay. It's n atoms, and it's all to all, but the fundamental underlying interactions are two-body, two at a time. But could we generate something like this? J plus cube plus J minus cube, which if you unpack it, actually has three-body terms over here with three atoms, for instance, all flipping their state at the same time. Or if you were ambitious, maybe you could say, maybe I could go to four-body over here, where four atoms flip their spin state at the same time. Now, when we first started thinking about this, my very, very bright PhD student, who's now at Caltech, Chingy Lo, he said, we should try this. And I said, it's got to be weak, right? Like, what's the characteristic energy scale associated with this? Well, it's n times chi2. It's a collective enhancement here. But I said, yeah, but if I go to like higher order and multiphoton processes, the chi is going to be a lot smaller. But the key point is that because it's not that one atom is making multiple transitions, it's that three different atoms. It means each step in that process gets a collective enhancement, and actually it goes like n squared chi3. And in the four-body term, it would be n cubed chi4. So even though chi2 is much larger than chi3 is much larger than chi4, you can imagine a scenario, but because our n is large, we can actually make these comparable to each other in energy scale. So we try it, right? How do we engineer this? We apply two dressing lasers, but now we separate them by three of the transition frequencies between spin up and spin down, or between the two momentum states. So 3 times omega z. We set it up so that the intermediate photons in this multiphoton process are all off resonance from the cavity. And so you sort of have a process where you emit a photon, and then stimulate emit. Okay. In this Bragg gradient, it means we're going to bounce multiple times. So not only we're going to create a sideband to the cavity, but that sideband is actually going to bounce off the density gradient. It's going to bounce off the density gradient in stimulated emission into this pump. Or you can draw all the intermediate states. I absorb a photon. One atom flips its spin state, in this case momentum state. Another atom absorbs that photon before it escapes, emits a red photon, and then finally that red photon gets absorbed and you get stimulated emission, and now all the atoms have changed their momentum state. That's the multiphoton process. It is a 3-atom, 6-photon process where we adiabatically eliminate the photons. That's what's going on. Okay. What about the two-body interactions? If you look here, there's also a process where an atom could emit a photon and another atom could absorb it and come back, and this gives you an exchange term, and the same here. And those are two-body terms. But it turns out that because of the detuning of this intermediate photon, this one is chi j plus j minus, and this one is minus chi j plus j minus, so we can actually get these two to cancel each other. We can get the two-body terms to cancel in this system. So you can write down the mean field equations of motion. Here are flow lines on the block sphere of how you expect the system to behave. There are 8 fixed points, 6 stable points at the equator, 2 trifurcation points at the north and south poles of the block sphere. So we can actually take data and we can actually see the expected sort of deflection if we prepare atoms at different points on the equator, a Bloch vector on different points on the equator, and then look at subsequent dynamics. We see deflections along JZ exactly as we expect. We also see that it's a resonant process. So if we break the 6-photon detuning by actually messing up the frequencies of our pumps by a little bit, by scanning that detuning, we see it only happens at a frequency here where it's exactly where we predict the 6-photon process to be. I'm not going to go into it, but let's just say we can also look at the physics and the flow near the trifurcation points, near the north and south pole. We can take data on it, but it turns out, I haven't told you, in this Hamiltonian, there's actually a phase degree of freedom that I haven't written down to this point. We can actually take advantage of that, see that respond to this, but this really opens the possibility of time reversal of dynamics by just changing the dressing laser's phase, which is really powerful because that's easy to do in experiments. So time reversal protocols are available. Lastly, I'll just say, I won't go into it, but we've also seen some evidence here. It's small, but it appears to be there, of a 4-body interaction with 4 atoms, 8 photons over here. So we have a signature of it. Finally, where are we going? We need to beat down some technical noise in order to harness all these XYZ Hamiltonians to look for entanglement. We're actually working on that. We're collaborating with Dan Blumenthal here at the University of California, Santa Barbara on some laser technology to help with that. It would be really interesting in the future to think about going to more momentum and spin states over here. You know, for instance, as you can imagine pair creation processes, but even going way beyond that. We think there could be a lot of fun, because this is almost like a lattice, but in momentum space over here. We have ideas for how to do a continuous QED monitoring of the phase of the matter wave interferometer and actually create entanglement that way, and lots of other ideas related to quantum simulation. I didn't do the work. I go down, I drink coffee, I talk at the whiteboard. It's a lot of fun. Great group of students and postdocs, as well as collaborators, so I want to thank them all. With that, thank you.
I try so.
Sure.
So, going back to the contrast and the effect of the interactions and the connection to the Moslem effect.
Yeah.
So you see something opposite, like the interaction, instead of giving a which way information, the canceling which way information, right?
So just to be clear, what we're doing is we are not, in that experiment, we're not trying to leak information out of the cavity. We're working explicitly in a regime in which ideally no information leaks from the cavity. It's just unitary dynamics that's responsible for this many-body gap that basically protects the system against states of lower symmetry. So one picture of this wave packet separation, instead of thinking of it as I'm separating, you can also think of it as what is the total symmetry of my state? And essentially the Doppler dephasing drives you to states of lower total J. And what we're doing is we're saying we're creating a term that looks like chi J squared, so that states of adjacent J actually detune. So here's my Dickey ladder. Normally dephasing due to Doppler broadening would couple this value of Jz to this value of Jz. But now because of that many-body energy gap, we push them off resonance. And that's what's protecting the coherence. So you can also think about it in a pure spin language and see where it comes from.
So can you read from the contrast information about the interactions?
Yes. So what that is telling us, oops, grab the wrong one. Let's go back to it. Turn it right here. What this plot is showing you is that if I make the interaction strength small or zero by not applying my dressing lasers, because this chi is proportional to my dressing laser power, then I can compare that to, in some sense, think of it as the characteristic frequency scale associated with the Doppler broadening, or equivalently the wave packet separation. And so what we're doing is, on this scale, essentially this curve is taken with no interactions, and the contrast goes away. And then what you see is, as you move along this axis, you go to a point where chi-in over this inhomogeneity actually crosses 1, and that's where you start to see a prolonging of the coherence over here. I didn't go into it, but in certain contexts, for instance, these oscillations you would refer to as Higgs oscillations over here, okay? So it's really related to that, in the fact that where you sort of turn on these interactions, you start to see it protecting the coherence, is telling you about the ratio of your interaction strength to the background inhomogeneity in the system. Does that help? Yeah. Sure, and then maybe I'll try and repeat it for people online.
No, it's okay. Cool talk, and lots of questions which we have to discuss.
Yeah.
I mean, maybe one of them, so when you had the 3 and 4 body interaction, it's really cool.
Yeah.
You always had pluses on the sigmas on all 4. Is this the only thing you can think, or is it just the easiest one to measure, or?
It's the one I know how to build. So what I would say is, sorry, I just want to get back to it. So the question is, we've basically have engineered things which are like we have a j plus q plus j minus q, but could you have something like jx cubed minus jy cubed? Like, do we know how to do that more general, like 3-body Hamiltonian?
I mean, you have 3 pluses or 4 pluses and
yeah. Yeah, and so the answer is, right now I don't know how to do it. But it's a question of engineering the right sort of multi-photon process that would give it to you. I don't know how to do it with just momentum degrees of freedom. I'm a little suspicious if you allow me to incorporate that one of the intermediate states involves going through a spin state. There may be a way that I can, by doing that, introduce additional pump tones or dressing laser tones that might allow something like that, but I don't know the answer. It would be great if there were. Like we know how to now generate all those two-body interactions that people have thought about in cavity QED. Like we finally have now in our experiment generalized that to XYZ Hamiltonians. Is there an equivalent of like XYZ Hamiltonians but for three-body interactions? I don't know the answer to that, but that'd be great.
So would it be possible to have this control, but also in the bad cavity limit, where you can engineer limb lab terms that are kind of this multi-body?
Oh, yeah, that's, yeah, great. Let's look at this, well, let's look at this one, right?
So to have a jump term.
Basically, you know, what would be the equivalent of the limb blood, something you would describe as limb blood, is if I were to shift my pump tones, say both of them to the left, so I stay on resonance, so they stay separated by 3 omega z, but I bring that intermediate photon close to resonance with the cavity. Then what that would do is it would open a collective decay mechanism of that pump photon, and normally we think of that as bad. But if there's some reason you told me that's good, that's easy, okay? That's easy to do. Now, I will tell you, one thing we tried is we tried quickly in the lab, I'm gonna mess it up, but I think we turned off that tone, if I remember correctly. We tuned this one away to try and put a second order sideband onto resonance, so you would have a Lindblad operator that's described by 2 photons exiting the cavity, or by, no, that's not right. 1 photon exits the cavity, 2 atoms flip their spin state. That's what it would describe. We tried, it was a gory mess. Maybe there's a fundamental reason, like you can't see it, because, you know, again, remember, you're always fighting against a single particle, well, single spin flip collective decay term if this one leaks out of the cavity over here. And so it's like, how do you separate those two out? But it's interesting, at least think about it at a conceptual level. Could you, for instance, have every decay photon gives you a spin flip of 2 atoms, 3 atoms, 4 atoms? Yeah. Mm-hmm.
I'm not sure if this is a big question or not, but other like effects of free body photons are like essentially different from two bodies. So like a way to, I don't know, but it couldn't possibly be a two body.
We don't know what it's good for yet. I will say that, for instance, if you're doing quantum simulation, there are things like charge 4e superconductors. And it might be that this is the kind of Hamiltonian you'd like to engineer if we want to do quantum simulation or emulation of such phases which have never been seen before. They've been proposed but never seen, right? So that would be in the context of quantum simulation. In the context of precision measurement, one thing that's interesting about this is if I imagine that all my atoms are at the North Pole and I turn on this 3-body interaction, you generate sort of what I'll call the 3-finger claw. So if you look at the probability distribution, actually you end up with sort of 3 legs that begin to sort of come down. It's a highly non-Gaussian state. And this thing I didn't have a time to talk about was this time reversal, because you could imagine that you run a time reversal sequence if you're doing quantum metrology where you evolve into this state, something perturbs your system, and then you time reverse it and ask to what degree do you come back to your original state. And it just turns out we have like really easy control of that, and that's not a given in every experiment. So that's an example in quantum metrology where it might be interesting.
Last question?
I have a question about your quantum resolution measurement.
Yeah.
On the slide in the figure, and it showed that you go below the percent on it.
Yeah.
It looks like it's some kind of voice score.
Yep.
Do you have an idea of what that voice score is?
Yeah. I'm showing you everything here. Darn it, I grabbed the wrong one again. I'm showing you the total measurement resolution. So sitting down about here on this plot is actually readout noise. Okay. We also use a QED measurement for our readout, but it's technical noise associated with the laser. The laser has frequency noise on it, and it gets folded into our measurement. The fundamental one is actually finite collective cooperativity parameter. If n times c went to infinity, oh my God, like we'd be good. But because of finite NC, it also sets a limit. It's just that it's better than what you're seeing here. But I just want to warn that NC is the thing you care about. If you can engineer a system, and you can do it in atomic systems, where if the atoms happen to scatter a photon into free space, it always returns to the same internal spin state. Then it turns out the requirement for hitting the Heisenberg limit up to numerical factors is that the single particle cooperativity needs to be larger than 1. That's actually really accessible in experiments. So if you have the right system, and that's not the systems I'm telling you here because we're exploring physics, and the goal here is to explore physics, it is possible with very accessible experimental parameters that you could imagine getting like really like hugging the Heisenberg limit. It's always a question of how close can you get, but I think you could get really close.